Have you ever wondered what makes the power in your devices smooth and steady, even though it comes from an alternating current source? Achieving that perfect, unwavering direct current is trickier than it seems. Ripple voltage in rectifier circuits is the small, undesirable alternating current component that remains superimposed on the direct current output after the rectification process. It is primarily caused by the intermittent nature of diode conduction and the charging and discharging cycle of the filter capacitor connected to the load. When an alternating current signal passes through a rectifier, such as a diode bridge, it converts the alternating current input into a pulsating direct current. However, this pulsating direct current is not perfectly smooth. It still has significant variations. To smooth out these variations and produce a more stable direct current, a filter capacitor is typically connected in parallel with the load. During the peaks of the rectified waveform, the capacitor charges up to the peak voltage. Then, as the rectified voltage drops, the capacitor begins to discharge through the load, providing current and maintaining the output voltage. This discharge continues until the next peak of the rectified waveform arrives, at which point the capacitor charges again. The difference between the peak voltage to which the capacitor charges and the lowest voltage it discharges to before the next charge cycle is what we perceive as ripple voltage. Factors like the size of the capacitor, the frequency of the alternating current input, and the resistance of the load all profoundly influence how quickly the capacitor discharges and therefore the magnitude of this ripple. A larger capacitance allows for slower discharge, while a higher load resistance means the capacitor discharges more slowly, both leading to less ripple. Full-wave rectification also inherently produces less ripple than half-wave rectification because it provides more frequent charging pulses to the capacitor, giving it less time to discharge significantly. To minimize ripple voltage in practical applications, engineers often employ several techniques. The most common approach is to increase the value of the filter capacitor, which provides a larger energy reservoir to smooth out the voltage fluctuations. Another method is to increase the operating frequency of the alternating current input, if possible, as this reduces the discharge time between rectified peaks. Additionally, incorporating a voltage regulator after the rectifier and filter circuit can further stabilize the direct current output, effectively reducing the ripple to very low, acceptable levels for sensitive electronic components. Understanding ripple voltage is critical for designing stable and reliable power supplies for virtually all electronic devices. A common metric used to quantify this ripple is the ripple factor, which is the ratio of the root mean square value of the ripple voltage to the absolute value of the direct current output voltage. For many sensitive applications, a ripple factor of less than 1% is often desirable, while less critical circuits might tolerate up to 5% or even 10%. Excessive ripple can introduce noise into circuits, cause malfunction in digital systems, or lead to overheating and premature failure of components. Ultimately, the careful selection of rectifier type, filter capacitance, and the potential inclusion of voltage regulation allows engineers to precisely control the quality of the direct current power. This ensures the delivery of a consistent and clean power source essential for the dependable operation of modern electronics, moving us from raw alternating current to the smooth direct current our intricate devices depend on.